When you do mathematics, do you ever wonder where it comes from? Was it discovered or invented? And if so, how and why? Equations are the heartbeat of mathematics, so where do equations come from? In this series, I've chosen some equations and I'd like to tell you a bit about them. This talk on the equation 1 + 1 = 2 is about the counting numbers we use as I attempt to answer the questions: how did early civilizations count? When did negative numbers and zero emerge? Can all numbers be written as fractions? What are rational, irrational and real numbers? And can one prove that 1 + 1 = 2? From earliest times, people have needed to count their sheep, measure their land and manage their finances. To do so, they formed stones into piles, carved notches on tally sticks, as shown here, and calculated on their fingers. And it was surely finger counting that led to our decimal system based on 10 and using only the 10 digits 1 to 9 and 0. But it's also a place value system, since the placing of each number determines its value. For example, the decimal number 5,157 means 5,000, 100, 5 tens and 7 ones, or 5 times 10 cubed plus 1 times 10 squared plus 5 times 10 to the 1 plus 7. Here the numeral 5 plays two different roles depending on its position, as 5 thousands and as 5 tens. And the advantage of such a place value system is that we can then write down any whole number however large and carry out our number calculations column by column. So how did our counting systems arise? How did early civilizations count? Let's look at some. Around 1800 BC, the Egyptians, who wrote on papyrus reeds, used a decimal system, but it wasn't a place value system because they wrote different symbols for 1, a rod, 10, a heel bone, 100, a coiled rope, and so on, repeating them as often as necessary. So the number below, reading from right to left, is 2 lotus flowers, 6 coiled ropes, 5 heel bones and 8 rods, or 2,658. Around the same time, the Mesopotamians, or Babylonians, were imprinting their numbers on clay tablets. They used a place value system, but it was based not on 10, but on 60, a method of counting we still use to measure time, with 60 seconds in a minute and 60 minutes in an hour. Then, using just these two symbols for 1 and 10, they'd write a number such as 1, 12, 37 to mean 1 lot of 60 squared plus 12 lots of 60 and 37 units for our decimal number 4,357. Moving forward by over 1,000 years takes us to classical Rome and to Roman numerals, a decimal system with letters representing numbers. But it's not a place value system because different letters are used for 1, 10, 100 and 1,000, and for 5, 50 and 500. So that, for example, 2026 is MMXXVI. Meanwhile, in China, counting boards were used for calculation, with small bamboo rods placed in separate compartments for units, tens, hundreds and so on. This was a decimal place value system, one of the earliest. And here each number came in two forms, vertical and horizontal, which alternate for ease of reading. So 1,713 is a horizontal 1, a vertical 7, another horizontal 1, and a vertical 3. And for the number 6,036, the 0 box is empty and the forms of the two sixes differ. A different method of counting was used for the calendar calculations of the Mayans of Mexico and Central America. These survive in a small number of manuscripts drawn on tree bark. Here counting was based mainly on 20, combining dots and lines to give all the numbers from 1 to 19 as shown. For larger number, they piled these numbers on top of each other. So here you can see 12 20s in red, plus 13 in black. corresponding to our decimal number 273. An attractive feature of Mayan counting was that each number also had a pictorial head form like the ones below. They also used a special symbol for zero, the shell-like picture on the left. And this leads us to the origins of the number zero. In India, around 250 BC, the edicts of King Ashoka, the first Buddhist monarch, were carved on pillars around the kingdom. Some of these included early examples of Indian numerals as a decimal place value system began to emerge, using only the numbers 1 to 9 and later 0. So how did zero arise? We've seen how the Chinese left spaces in their counting boards, while other civilizations left spaces in the sand to distinguish between numbers like 35 and 305. But gradually special symbols began to emerge. Here's a 9th century cave in Gwalior in India, where 270 is clearly visible. But there was great excitement when some birch bark, undiscovered for over 100 years, was found recently in Oxford's Bodleian Library. With many blobs on it representing zero, it predates all other known appearances of zero by several centuries. The number zero plays two roles, as a placeholder, as we've seen, but also as a number in calculations. Positive and negative numbers were already being used in money markets for profits and debts. And around AD 600, rules for calculating with them and with zero were given by the Indian mathematician Brahmagupta. For example, the sum of zero and a negative number is a negative number. A negative number taken from zero becomes positive, and so on. The only problematic rule was the last one, relating to division by zero. This is forbidden because if we cancel the zeros in an equation like 4 times 0 equals 9 times 0, we get 4 equals 9, which is nonsense. Here's how our number systems developed over the centuries, leading to the numerals at the bottom, which we can clearly recognize. Also developing were the Arabic numerals on the right, which are still used in countries of the Middle East. But it took many centuries before what we now call the Hindu-Arabic numerals were fully established. This 16th century picture represents arithmetic and contrasts the modern algorist with his Indo-Arabic numerals on the left with the old-fashioned abacist with his counting board on the right. And it was also around this time that equations like 1 + 1 = 2 were first written down, as in this textbook of 1557, showing the first ever and rather long equals signs. What about fractions? The civilizations we've met certainly used them. A fraction is a ratio of the form a over b with b not equal to 0. And rational numbers are numbers that can be represented by fractions. For example, the rational number 0.5 is represented by many fractions, such as the 2 shown here. An irrational number is then a number that cannot be written as a fraction. For example, the square root of 2 and the circle number pi. Real numbers are numbers that are either rational or irrational and often appear strung along a line as shown here. But such a description is problematic because earlier we defined an irrational number to be a number that isn't rational. So what exactly is a real number? Such foundational difficulties were eventually resolved in the 19th century, in particular by the German mathematician Richard Dedekind, who defined an irrational number in terms of two sets L and R of rational numbers. For example, for the irrational number square root of 2, L consists of all rational numbers less than root 2, while R consists of all those greater than root 2. And this approach successfully dealt with all the difficulties. Finally, in the early 20th century, in a 3-volume work on the principles of mathematics, the Cambridge logicians A.N. Whitehead and Bertrand Russell attempted to place the whole of mathematics on a strictly rigorous foundation. We conclude by showing their proof that 1 plus 1 equals 2, which isn't reached until well into volume 2. As they jokingly remarked, the above proposition is occasionally useful. Thank you for listening.